So to start off our discussion about aromaticity, we're actually going to have to step outside of Lewis theory. And as an organic chemist, I'm sure it pains me deep inside to know that we're going to trash on Lewis theory before we can start talking about aromaticity. So aromaticity is not really something that is truly predicted by Lewis theory. Now, organic chemists will argue with me about this, but they're wrong. The reason they're wrong is that one of the key assumptions of Lewis theory is that when we form these bonds, we're localizing electrons between the two atoms, and this is what gives rise to valence shell electron pair repulsion theory, or VSEPR. So we kind of need a quick primer on molecular orbital theory. Now, the full caveat here is that if you're taking organic chemistry, you're going to know what I'm saying is really grossly oversimplified. But if you're an organic chemistry student, you've probably only seen people talk about molecular orbital theory in kind of this abstract hushed tones because it's really hard to explain. So what happens, what truly happens, is that atomic orbitals are probability waves. So your SPDF orbitals represent the probability of finding the electrons. And because they are probability waves, we can add and subtract the probabilities to get the new probability. Now, a molecular orbital is composed of the addition and subtraction of individual atomic orbitals. So the simplest molecular orbital we can build is something like hydrogen. Hydrogen consists of two 1s orbitals that look like spheres. Now, what we can do is we can take these 1s orbitals and we can add and subtract them. If we add them in this case, we have an s and a p, they will constructively interfere. And what we do is we see the electron density kind of shift, the probability of finding electrons shift being between the two nuclei. So this is the 1s plus the 1s of the other hydrogen. Now, is it always true when you add you get constructive interference? No, but for simplicity's sake, we'll say it is. Now, the other option is we can subtract them, and when we subtract them, what we do is we take the probability here minus the probability here, and we actually get a gap between the two orbitals. So this is the 1s minus the other 1s. This draws the electrons together and lowers the energy of the electrons that are in them. So we would call this bottom orbital here a bonding orbital. Any electrons that drop into a bonding orbital increase the stability of the molecule. The one up here, which actually increases the energy of electrons, is considered an antibonding orbital. So what dictates if it's bonding or antibonding? Well, our baseline here is our atomic orbitals. So the electrons, their wave functions will come together and they will generate the bonding and antibonding. If the electrons overall lower their energy, meaning that based on their starting atomic orbital energies are more electrons in lower energy than they start out in, we will get a molecule that is stabilized and we get bonding. If we have just as many electrons in antibonding as we do bonding, the molecule falls apart because why bother if you're going to come together and it not really benefit you? In particular, if we have more electrons in antibonding than we do in bonding, we end up generating a molecule that just falls apart. So we can do any molecular orbital using any atomic orbitals. And it's this addition and subtraction of wave functions that is going to give rise to the molecular orbitals we see in molecules. And it's also going to kind of help us explain what's going on in terms of aromaticity. So the next video, let's talk about what happens if you have a whole bunch of atomic orbitals sitting around a ring.